So suppose most of the audience is aware of, let's say, the copper interconnect bottleneck at data centers, and specifically when you're using AI algorithms, it becomes more prominent. And photonics is a solution there, and it really requires photonics to grow to higher volumes. And what we see is actually still, we believe, kind of a hidden problem, and that is that the accurate placement of photonic components needs to be quite accurate. And well, it can be done, but it really requires dedicated tools to do that, usually something like an micro tool. It's really slow and does not scale. So on top of that, it's also quite costly. And well, if your system becomes more complex, the active alignment that's used becomes also very impractical to be used. So we don't think that that's a good way forward. We need a solution that does scale, and what we want to propose is really use, let's say, the existing die-attach tools that are out there for electronic components. They usually have like 3 to 10 micron accuracy, and we want to use those. And there's a large variety of tools available, ranging in different speeds that they can run at. And what we do at PhotonPoser is that we add an auto alignment layer to the interposer, and whenever you have like within the 10 micron accuracy, this structure will guide your die to a more accurate position in the range of 100 nanometer. That's in essence what we do. Obviously that goes a lot faster, and the standard tools making it much less costly, and we're really looking at cost of sub dollar cents. That's really a target that we have. So on top of that, we also came up with an improved way of doing edge coupling, and can get really low loss there. And on both of the topics, we have filed patents. So if you look at that, obviously AI market is booming, and it's going like crazy, I would say. And we see that billions of dollars are being spent in developing the best chiplets out there for this particular case. And there are well-funded startups like AL Labs, Light Matter, Celestial, that are trying to get into that market. And obviously all the big guys are also working on that. But so far, we've not really seen a good solution to do the placement at a scalable way. And if you look at what we do, it's going to be low cost and low loss, and that gives you more possibilities. So you can do another trade-off. Either use a very large PIC with a low yield, or use divide it into many small PICs and with a much higher yield. That might be a much better cost trade-off. And moreover, we are able to integrate different types of photonic or even electronic chiplets. So that gives you much more flexibility and architectural freedom, which also can give you an additional performance boost. So if you look at the technology, I'm not going to show you the patented technology here, unfortunately. And there are many different types of integration schemes possible, but here's just one example. So here we start with a standard electronic interposer, which has through silicon vias and some RDL layers. And we put a photonic layer on top of that. So there are some waveguides, the alignment structure is not shown here, and there are cavities where the dies will be placed at. So you see here a top view of the interposer, where there are quite a lot of places where you would need to place the picks. And obviously we do that then with these standard die attach tools. So you get an electronic connection at the bottom, and the waveguides are coupled at the edge of the chip. And finally we can also hook up a fiber, either with a grating coupler or edge coupling. So that's in essence what we do. As the topic of today is on AI, let's take a look at an example from an AI solution here. We'll look at a Blackwell GPU. It has an electronic interposer, not a photonic interposer yet. But it's made by TSMC. TSMC is doing a lot of interposers, and they have 3 flavors, and the last one is called CoWoS L, and that is also used for Blackwell, along with a co-packaged optics solution. And if we look at that, here's kind of a cross-section of that, where we have the CoWoS layer, which, let's see if we can get the laser pointer. So it's basically this part here, where there are some simple chiplets integrated into a molded part. So that's the black part. And then it's, let's say, wrapped with some RDL layers at the top and at the bottom. And that's basically the interposer as it's done nowadays by TSMC. And then we have on this side here, we have a PIC with a driver, which is bonded on there with at wafer level. And that's a chip that's going to be placed on the substrate inside the package, on the edge of the package, basically. And there you also hook up a fiber, either again with grating coupling or with edge coupling, as it's shown here. But what this still gets is, like, we have short wires for the HBM that's connecting here, but for getting from the GPU, which is called logic here, to go to the EIC, it's a longer path, and that is requesting some more power, and might also impact some speed with going through all of those micro bumps and then some of the larger bumps on the substrate. So what we propose here is that you could add a photonic layer actually to this interposer. And so it's here it's done partly, not on the whole interposer, depending on what the need is. And then you move this PIC and its driver into the interposer as well. And in that way, you can shorten that path between the GPU and the EIC, and potentially get some speed increase and save definitely something on power. Besides that, it also makes the package somewhat smaller. So, but that in itself might not be enough to justify the cost of adding this photonic layer. So what else can we do? And here is another example that what we can do is just adding extra high bandwidth memory here. And that's then on a longer distance, so that has some more problems in the connection. But when we do this over a waveguide, we can go for this longer distance. And even more, we potentially can go at a higher speed, and we can also add more bits per cycle when we have bits multiplied over the waveguide. So that's certainly a benefit. And then there is a study out there that shows that when you quadruple the amount of HBM around the GPU, it can basically run larger matrix multiplications, and that would allow to halve the amount of data transfer that goes in and out of the board. And as that is your bottleneck, that could also significantly improve the AI performance. So, and obviously if you have already this HBM going over a waveguide, then also the other one probably can be replaced as well, and using the same way of working. So that is basically what I want to show you today. So we have a photonic interposer that provides a path to high volume photonic systems, not just for AI applications, but can also be used for datacom or photonic computing or quantum computing. It's a simple, low-cost, high-yield solution. We don't need a lot of masks to make these, at least with respect to the photonic layer. And it's going to be low loss and high performance. So with that, I would like to conclude, and if there are questions, you can ask them now, but I'm going to be also at Big Summit this week, so if you're there, you can ask me in person, but you can also send me an email. Really appreciate the feedback that you have. So if you have an application, talk to us. If you're a supply chain partner who sees that you can add value to this, let me know. And in case you're an investor, we're still closing our round now, so if you're interested, you can still get in. Thank you for your attention.